So first and foremost, we are talking about the definition of a derivative and what a derivative actually is. So derivatives are one of the main things in calculus that we are going to be working with. And it, let me see where my notes are here too. I need to get mine. Okay. So the definition of the derivative, what it represents is the slope of the tangent line. So a derivative is known as the slope of the tangent line. Okay, now what is that? What is a tangent line? That's like a geometry concept. So kind of coming through all of that together is something we're going to be having to like picture this and work with what it is and what we are finding. So we did limits last unit, and limits kind of help set up our definition of derivative on all of this. And there are some notation stuff that we're going to be talking about with this as well. So when we look at this, we have to look at it from the perspective of limits. So let me get that definition real quick, because if I don't... All right, so a derivative comes from a limit, and it is a notation that we have seen before. Okay. So the derivative is known as the limit as delta x approaches 0 of f of c plus delta x minus f of c over delta x. Okay. And we're going to work with that definition just for today only. Okay. And we will talk about what we're going to do with that. It actually is very similar to what you did on your challenge problem on your test if you tried that. It was that kind of notation. And we're going to work through that like once to see what it looks like and why we have easier ways to do it. That is kind of the point. So there are some different notations that you can use for derivative. So we are used to seeing f of x. So a derivative we can write as f prime of x. Okay, so that's a notation for our derivative, f prime of x. You can also notate derivative as dy dx. A less common derivative notation is delta y over delta x. These two are going to be more common. Or you could see y prime as well, similar to f prime of x. No? Okay. These are just different ways that you are going to see derivative notated. And you're going to, as we get through this unit, you're going to see most of those different notations as we go. So it will just kind of vary between them. It could say f prime of x. It could say g prime of x. It could say y prime. It could say dy dx. So you're going to see just a lot of the different ones in there. Zach?
What does c represent?
What's the c represent? Any constant, so any number. So we're going to see what that looks like here in a minute in an actual example. And then it'll make a little more sense. It could be like a 1 in a problem. Yep.
So delta x means derivative of x?
Mm-hmm.
Limit of the derivative of x as it approaches 0.
So delta x does not mean derivative by itself. Delta x means the change in x.
Okay.
Okay. So we've written this down. What does it mean? Okay. Let's talk about that. Okay. So real quick, just want to talk about what does this actually mean and what does this actually look like before I do example 1. This is like one of the few places where I will tell you, like, put everything down and just look at the board and don't write anything down. Don't try to draw yourself a picture. Just follow. Okay? Are we good with that for the moment? All right. So here's where we're all at. Okay? In the past, in algebra, if you had a line, okay? If I had a line, do you know how to find slope?
Yeah.
We do. What's the formula for slope?
Rise over run.
Rise over run, or y2 minus y1 over x2 minus x1, right? Another way to notate slope is this. Have you ever seen that notation for slope?
Nope.
It's called the change in y over the change in x. Basically, it's saying the difference in your y values over the difference in your x values. It's the exact same thing as seeing that formula. It's any y value, the change between them, any x values, change between them. Okay? This is something that we just saw in our derivative notation, right? Okay? So this is what this is. Derivatives are basically finding slope when you cannot use the slope formula. Okay? If you wanted to find the slope of any line like this, you would find 2 points and you would use your formula. We all know how to do that from algebra. What if, instead of finding the slope of a line, I asked you instead, let's say we have a parabola. Okay? And let's say I wanted to find the slope right here at that point. Do you know how to find slope at a point?
Use the derivative thing.
That's where we're getting, but this is why. Okay? Right now, if I wanted to find the slope at that point, I can't find the slope at one point, can I? No. I know how to find the slope between 2 points. So what if I drew a line and said, what if, let's say I drew the line between, let me see, I can't connect my dots right here. If I drew the line here, and I found the slope between those 2 points, like I just picked another point so that I could find the slope, is that going to be the exact slope at the first point that I had?
No.
No, it'll be close, right? But not exact. What would be the exact slope at this point would be the slope of the line that just touches at that point and goes through. Okay? This kind of line, if you don't remember from geometry, is called a tangent line. Okay? A tangent line touches the curve at one point only. Okay? But again, that tangent line, it only touches it in one point, so I still can't use my slope formula, right?
Right.
Okay, so what you would do, just a minute ago I said, what if I drew that other line and I made another point through here, and I said, well, the line through that's going to be closer. How do I get closer and closer and closer to that point?
You keep going to the top of it.
Okay, I take this point here and I move it closer and closer and closer until I get almost till those points are right on top of each other, right? And that would be the most appropriate thing. Okay? So what you are telling me by saying making that point closer and closer and closer, this is where this notation comes into play. A limit is a prediction. Yes? Delta x is the change in x, or the distance in x between these points. This is why we say delta x approaches 0. Because what you're doing as you take that point and bring it closer and closer and closer is you're saying, I'm trying to make the distance between those points as small as humanly possible. Or it's getting closer and closer and closer to 0. So what the derivative allows us to do is when I don't have 2 points and I can't use 2 points through it, it allows me to find the slope at one specific point. So that is what we're doing. Derivative equals slope. All right? Derivative equals slope when it's not a straight line. Okay, so if you get nothing else out of today, derivative equals slope. Just go with it. Okay, it's the slope of a curve that is not straight. Okay, so going back to my original page here. Let's go back and look at what it would look like if I had to do a limit definition of a derivative. Okay, so here's how we're going to do this. We are using our notation in part B to find the derivative of this function using the limit notation. So that is the limit as delta x approaches 0. And we are going to use that f of something notation. Okay? All right, so if I was to do that, here's the notation. I'm just copying it down from part B. Okay, that's our limit definition notation. I would like to find the derivative or the slope of that. And the slope if I graph this is a parabola, right? Let's just draw what that would look like. That's a parabola that looks like this. What is true about the slope as I went around that curve? Is it the same for every point? No, it's different, right? If I found the slope at that point, it would be different than the slope at this point. It would be different at the slope at this point, and so on as we go around. Okay? So our notation here is going to give us an equation that gives us the slope at any value of x. So what that's telling me is I don't know what c is, but I would like it to be any value. So we're going to leave it generic as c. So we've done this before this year. It's been a while. But what does this kind of notation mean? No. What if I said just this? Let's go with something simpler. What if I said f of 2? What does that mean? What should I do?
C is 2.
That means take out the x in my equation and put in 2. All right, so what if I said f of x squared? What does it mean? Take out the x in your equation and put in x squared. All right, so using that same idea, what does it mean then for me to do f of c plus delta x? Take out the x and put that in. All right, so looking at my original function here, just that purple box, I am taking out the x in my equation, and in place of x, I am putting what? C plus delta x. Okay, now let's look at the next part. F of c. What does that mean? Take out the x, put in c. So what's that going to look like in terms of my equation? This is my equation here. If I take out the x and put in c, what's it going to look like? C squared plus 1. That's all over what? Delta x. Now, we've done this kind of problem before, but let's work through it again. We haven't done it with c's. Okay. What can I do to simplify the top of that fraction?
Put in your...
Not yet. If I put in the 0 for delta x, that will give me 0 on the bottom. I don't want to do that yet. Okay, so I'm going to FOIL that all out. All right, so let's just see what happens. If I FOIL c plus delta x times c plus delta x, what's c times c?
C squared.
All right, c times delta x on the outside.
Plus C delta x.
Okay, and then the same thing on the
Plus
inside.
C delta x.
All right,
Plus delta x squared.
okay, you are.
I'm on fire.
All right, and then I've lost space there, but really what's still there? Minus that. So that's going to be minus c squared and minus 1.
Cancel the C squared.
All right, that's all over delta x, and as David just said, the c squared cancels. Oh, I also lost that plus 1. Did anyone catch that with me? I lost my plus 1 there. What else cancels? The ones cancel.
And then you can combine the C delta x.
I can combine this. That would be 2c delta x.
And then you can also take out it.
And I can take out a delta x. So if I factor out a delta x, I'm left with 2c
Delta x.
plus delta x over
Delta x.
delta x.
Cancel the delta x.
Okay? So what am I left with?
2C delta x.
All right, now what do we do with limits?
You substitute delta x.
All right. Which means that my final answer here is what?
2C.
2c. So that tells me that if I went around that U shape that I drew, at any value for x or c, that it's going to be 2 times that, and that's going to be my slope. So at -1, my slope would be -2. At -2, my slope would be -4. At 0, my slope would be 0. Exactly. Now, this process. Anyone really like doing that whole thing?
I personally enjoy
That
it.
is actually low.
I personally don't like it either.
Low key, that's like
Okay.
satisfying to do all.
It is a little bit satisfying, okay? There is a part of it that's satisfying. Now,
It's like Christmas morning.
The good news for us, the good news is that there are shortcuts. Okay? Do you think that we have to do that again to make us appreciate the shortcut?
No.
All right. So the good news for us is that there is a shortcut. We're going to skip example 2 and go to the back. Okay? Of course it does. Work gives you a headache. All right. Here are our beginning basic derivative rules. These are our shortcuts. So what we've learned so far is that the derivative equals slope and that you get a derivative from a limit. We don't love the limits and all the work, so we have shortcuts to them. Okay? So here are our shortcuts for any constant value. For any constant value. What's a constant value? It doesn't have an x in it, right? It doesn't change, it stays the same. Okay, so what our notation is going to be for this? For the derivative of any constant. This is another derivative notation. The derivative of a constant is always equal to 0. Always. So if I ask you, for example, next to this, I give you f of x is equal to 7. This is a constant, right? There's no x in it. What is the derivative of 7?
0.
0. Yep. The derivative of any constant value is 0. So if your function is y equals 7, the derivative of it is 0. If your function is y equals -3, the derivative of it is 0. 0.
Derivative of -47 is 0.
The derivative of any constant value is 0. All the time, every circumstance. Okay? But that's when there's no x in the formula. Okay?
This means it's a straight.
It's because it's a straight line, right? So here's why, guys. What kind of line is that?
It's a basic line.
It's a horizontal line.
Straight line.
What is the slope of any horizontal line?
0.
0, so that's why that's true. Any horizontal line has a slope of 0. Okay? Power rule is the second one. This one, number 2, is going to be one of the most helpful rules to you as you go through this. This is what helps us avoid the notation that we did on the last one. Okay? So this notation is not going to make sense for just a moment, but just stay with me. Okay? So write that down for a moment. This is our power rule. And then we will talk about what it means. Oh, whine about it. Do you want to go back and do the limit thing again?
Don't whine about it, Jackson.
This is actually a very easy rule. Okay? It doesn't look easy until you kind of talk about what it is in words. Okay?
But can I guess?
All right, so the power rule is x to any exponent. What do you think is happening, David?
I think that the derivative of the value of the exponent is equal to the exponent times, I don't know what the n is.
Okay, so just tell me what that would look like then.
I'm going to go with 1.
No.
So
Because I saw n minus 1.
wait,
on top.
so the n is the n, 3, so it's 3 minus, so it's 3 minus 1. Where?
Yes. Okay, so what you're looking at here is you start with x to a power. The derivative of it, you take that power, put it where?
Right there.
In front.
What is the n?
The n is the power, the exponent.
That's why I got
So the 3 in that one. So you take the exponent, you put it down front,
Oh, so it's 3.
you leave the x, and you subtract 1 from the exponent.
So 3x.
So using this example here, when I look at x cubed, I take that 3, I put it down front,
3x squared.
and I take 1 away from the exponent.
3x squared money.
Okay?
It's kind of obvious.
So let's do a different one of that. What if I told you x to the 5th?
5x to the 4th.
5x to the 4th.
Boom.
What if I told you x to the -2nd?
Oh, because it's minus.
-2. -2x to -3.
-3. Yep. Yes, sir.
So if it's like that symbol, what is the d? What is all the d over dx?
Okay.
What does that mean? Like what is that?
This is just saying if I ask you to take the derivative of this, it is equal to 0. If I ask you to take the derivative of this, it's equal to this.
So d over dx equals derivative.
Yes. Take the derivative of this. All right. 2 more basic rules for today, and then we're spending some time practicing them. Okay?
No.
All right. Last 2 basic rules for today. This one is called the multiple constant rule. This is saying if you are taking the derivative of something that has a number in front of it, you can simply pull the number out and take the derivative of the function. Okay? All right, that notation will not make a whole lot of sense to you. It is the difference between something like example 2 and example 3. When you have an x cubed, we just learned you bring the x or the 3 down in front and subtract 1 from the exponent, giving you 2. Well, what if there was a number in front of it? Okay? What that tells me is I can split those up. That's what this rule is saying. I can leave the 2 and take the derivative of the x to the 4th like I already learned. So what do I do with the x to the 4th?
You do step number 2.
Yep, so I bring the 4 where?
Down
In front of the x, and I do what with my exponent?
And then you
Subtract 1. And then you just multiply those together. That's what the constant multiple rule says. So it would be 8x to the 3rd. So the constant multiple rule is fancy notation for ignore the constant and multiply it by your answer at the end. That's all it means. Okay? And then the sum and difference rule, I can write down the notation for you, but this should make sense. When it's sum and difference, in other words, you have multiple terms added and subtracted together, you just take the derivative of each term individually. I'm not even going to write the rule for this one. How do I take the derivative of x to the 3rd?
Do the 2.
3x to the 2nd.
3x to the 2nd. Now, think before you do the 4x one. What's the exponent on the x?
1.
1. So let's think through this one.
It's going to cancel out.
It's going to multiply by
It's going to
the...
go to 1. Any exponent to the 0th power is going to be 1.
Okay, so here's how this works. You take that 1 exponent, just like in the power rule, and you bring it down and multiply it by the number in front. That's still negative 4, right? Usually how you think about it is that you keep the x and subtract 1 from the exponent. But if I subtract 1 from the exponent, it gives me x to the what?
0 power.
0 power. If x is to the 0 power,
It equals 1.
it's just the number 1. So really what happens to the
It
x?
stays.
It goes away.
I was going to say 4 stays.
And then the third term, what's the derivative of any constant?
0.
0. So do I have to write 0?
Nope.
No.
Well, you can if you want.
I can if I want, but I should then combine it with the 4.
I was right about the exponent.
Yes, but you yelled it and it didn't make sense to some other people. Okay. All right. For the sake of having this written down for later, we are also going to write down real quick the derivatives of the sines and the cosines. We'll fill in some of this later, but we're just going to do sine and cosine. All right, so on your table, the last thing here, the trig derivatives. The derivative of sine is cosine, and the derivative of cosine is negative sine. Okay, we'll fill in the other 4 later, but just start getting those in your head. Okay? All right, so now here we are. We're just going to spend a little bit of time practicing, and then we'll be done. Okay? So let's take a look. Let's start easy. Let's look at 3 first. Okay. 3 is a rather straightforward one. It's currently x to the 1. Okay, think back to the power rule. What does it say to do with that exponent? Bring the number down front. So, and we're also going to practice notation, guys. We are not just writing this blankly in space. If my function is y, what is my derivative notation? Y prime. Okay, if it's f of x, it's f prime of x. So start writing down your notation because otherwise I don't know what you're talking about. I don't know what you're referring to. So the derivative is y prime. What does my rule say for this? Take your exponent,
Bring it to the front.
bring it to the front, keep the x, and do what with your exponents?
-1.
-1, which gives me x to the...
Makes the x disappear.
So what is my final answer for this?
Y equals 1. Y prime equals 1. What's the prime again? So I missed that part.
That just means the derivative of y. So
Is
you
that a
have...
1?
It's like a...
It's not a 1.
It's like an apostrophe.
Ah, money.
It's not like a 1. Yeah. So let's go back and try number 2. Before I can do the derivative on number 2, I have a little simplifying to do first. What does the cubed on the outside mean? Cube 2x. So what is that the same as? In just a minute. But what's 2 cubed?
8.
What's x cubed? X cubed. Now I can use the power rule. Okay? So notice, again, notation is important with derivatives. So I still wrote y there. Why did I just write y?
Because it's not y prime.
It's not y prime yet. I just was simplifying the function. Now let's take the derivative, y prime. Power rule says to do what? Bring the 3 to the front. If there's a number there already, what do I do with it? Multiply. So when I bring that 3 down front and multiply it by the 8, it will give me 24. If you don't like going straight there, you may take a minute and just say that 8 stays by itself. Now I'm going to take the derivative, 3x. What do I do with the exponent? Subtract 1. Gives me 2. So my final answer, 24x squared.
8 and 24 is the same problem.
Okay? Let's go back to question 1. There's a small amount of rewriting to do on that. When x's are on the bottom, what kind of exponents do they indicate? Negative. So on anything that has an x on the bottom, I need you to rewrite it first. You might want to make yourself a note here. Anything that has an x on the bottom, you need to rewrite it using exponents first. So when x is on the bottom, this is the same as x to the -1. I need it to look like that before I can use the power rule on it, right? So now the power rule says, now we're doing derivative. What's my notation for f of x? F prime of x. Okay, so I'm going to show my derivative notation. What do I do with my exponent according to my power rule? Bring it to the front. Keep the x. What do I do with my exponents?
Subtract it by 1.
Okay, so what's my exponent now?
-2.
All right. Now, unfortunately with this kind of question, we rewrote the original so we could see it with an exponent. We now need to rewrite our answer to be proper with not negative exponents. So what is my final answer going to look like on this? Where's the x to the -2 going to go? On the bottom. What's going to go on the top? -1, right? So we kind of take it out of the fraction notation to do the derivative, put it back in the fraction notation to get your answer. That one is very similar to 4. So I'm going to help you rewrite the original question right now, and then I want you to see if you can find the derivative. Okay? Because that x squared is on the bottom, I can rewrite this as 4/3 x to the what? -2, right? Notice that I made the x with a negative exponent, but I left the numbers as a fraction. That is the simplest way to do it. All right, take a minute and try to get the derivative of this using your power rule.
They got one, so I gave it up.
All right, so let's go with the basics on this. There's a number out front, so when I take the derivative, I leave the number out front, right? So I leave the 4/3. What do I do to take the derivative of that? Bring the 2 down front, and this is going to be multiplied by our constant. And what do I do with my exponents now?
You bring it to the front.
I brought it in front,
Subtracted by 1.
subtracted by 1. So what's my exponent now? -3. Okay, to clean it up, I have 2 things to do. I have the numbers to multiply out front. What do I get when I multiply those together? Okay, -8/3. And where does the x to the third go?
With the x on the right, but I don't know where the...
Because of the negative exponent, it goes where?
To the bottom.
On the bottom. All right, before we look at anything else,
Completely wrong, so let's go.
before we look at anything else, what kind of questions do we have on any of these so far?
Is this all we're gonna have to deal with?
It's very, very algebra. Like, once you learn the rule, it's a lot of algebra. Okay? So it's definitely different looking than limits were. All right. Before we go to the next page, I want to fill in the entire trig limits table above. Okay? So, real quick, we filled in the derivative of sine is cosine. The derivative of cosine is negative sine. Okay, so fill in this table real quick.
So it's cosine
The derivative of tangent is secant squared.
Are you showing us this, or were we supposed to know this?
Oh, you're not supposed to know
There's
this.
no way for us.
I was about to say.
Okay, so for trig derivatives, there's no like special rules for these other than like this is what the derivative is. Like if I ask you what is the derivative of sine?
Just write it down and use it.
Cosine.
There we go.
Like this, we're going to get to the place that we memorize these. I'm not going to make you know all of them at once. But like, so here's the thing with the rules. Like we learned those 4 rules to begin with. I'm never going to like sit down and say, what is the product rule? Like you have to use it, or what's the power rule? You have to use it, but you're never going to actually like write it out. It's not like you're memorizing them that way. It's like you need to know what to do with an exponent one, but you don't need to ever write out the rule. These are the only rules that you are going to have to memorize. Maybe the product and quotient that we do in a little bit, but the rest of them are very process-based. They're not like, this is what do I do, not here is the memorizing the rule thing. Okay? So these we're going to get to memorize, yes, but again, they're not like a rule. This is just what the derivative is. Just is that. I could show you how to get them all, but I don't think you necessarily want to do that. I'm just taking a guess. Okay?
Is cosecant x like the trig negative cosecant x?
Yep. I didn't make this box big enough. Cosecant's derivative is negative cotangent times cosecant.
Yeah.
Yes, like you know that.
Then it's secant x times tan x.
Cotangent is negative cosecant squared. All right, so like I said, these are just our trig derivative rules. So when you are asked the derivative of something that involves trig, refer back to this, which we're about to do here in just a second. All right?
That's a long lesson.
Yes, what am I supposed to do with like 45 minutes? Just let you look at your phone, which you do during the lesson anyway?
No, I'm actually
So.
having a good time this morning.
Oh, good.
Okay, Miss Leininger, I've never actually focused. Oh, please don't throw this away.
Okay, write it down.
I would have focused this hard. But I'm on a roll today.
No, I just feel so blessed.
I've been trying to get it on track,
All right, make sure you got the trig derivative rules down. We're going to use them on the next page.
What's the
And
cosecant line box?
I couldn't fit it. I made the boxes too small. That's what happened. All right,
all right, I'm in there.
next page. Okay, these work the exact same as they do with the other ones. So like if I ask you to find the derivative in question 5, there's a constant in front of a sign. The constant works the same way we do before. It's just that I have to refer back to the table. So when I'm finding the derivative of 2 sine of x, I'm just going to say that's 2 times what's the derivative of sine? Go back and look at your table. Cosine.
So, are you going to give us that chart, or are we going
You're going to memorize it eventually. Right now, for homework and stuff, use the chart. What's the constant in front of number 6, actually?
I thought the 2 goes to 0.
That's the answer?
That's if you're taking the derivative of 2 by itself. If it's a number multiplied out front, it's multiplied by the derivative.
So that's the answer?
That's the answer.
Okay.
Yeah, the trig rules, there's nothing to do with them. You're plugging in what is the derivative of that. There's nothing to it.
So 6 would be negative side then.
Okay, so real quick in 6, first, what's the number out front of the cosine, really?
1.
Okay, so that's like a 1/2. Yes?
Yes.
So when I take the derivative, I'm thinking, I leave my constant out front. Now what's the derivative of cosine? Negative sine. So the only thing I need to do to clean that up is to put the negative in front of the 1/2.
Yes, I need Andrew Lowe. He's leaving for an appointment.
Okay, yes ma'am, thank you.
Thank you.
So 7 works very similar to that. You just do one term at a time. So remember, you take the derivative of that term separately than that term. That's what that last sum and difference rule said. You can do 2 terms separate. So let's worry about one at a time. Secant x. Look at your chart. What is your derivative of secant? Tangent x, secant x. Now worry about this term. That one has a constant out front. So when I do that, I leave the constant out front, and then I worry about what is the derivative of cosecant. What's the derivative of cosecant according to our chart?
Cotangent x cosecant.
Negative.
Sorry. Jeez.
All right, so all I have to do to clean that up is what?
Goes down bad.
Okay, this becomes like a -3. So if you want to write another line, do it. If you don't, and you just want to erase in here and say that becomes -3, great. Now, sometimes it may help you to simplify first. We don't know how to do derivatives where we multiply things together yet. The homework will be, yep. So we don't know how to do things that multiply times each other yet. Do we remember what the definition of tangent was from last year? How we could represent it?
Something over something.
So we can represent tangent as sine over cosine. Cotangent we could represent as the reciprocal of that, which means what?
Cosine over sine.
What does that mean I can do with these fractions? What does this simplify to? What happens to the cosines and the sines?
Cancel.
Which means what does this simplify to? 1. So what we've just found is the function simplifies to 0, or to 1. What is the derivative of 1? 0. Okay. So sometimes you can simplify first using algebra. It's easier. 9 is actually very similar to that. Anyone remember what sine squared plus cosine squared is the same as?
That's
It's one of the trig identities you used last year.
Oh, it's
Oh, it's one of the trick identities we used last
Wait,
year.
what'd you say?
9, question 9. Sine squared plus cosine squared is a trig identity.
yeah. I
Tangent
remember
squared x.
tangent squared.
1.
No.
Oh,
Oh yeah, that's right. Because I remember using it when we
Know these?
There's a few small ones that will be helpful, like that. Or like knowing tangent and cotangent are the reciprocals.
That was fire.
So if that simplifies to 1, what's the derivative? 0. All right. Last couple and I'm done.
Oh.
All right. Question 10. Right now the way it stands is a little bit ugly. What did we do when x's were on the bottom before?
Pull it up and say.
Kind of pulled it up with a -1 exponent, but we don't really like that with all of that up front. Remember when you were dividing by x
Yes.
or dividing by one thing?
Yeah.
That's just really 3 separate fractions. It's just this, this, and that. Now, why do I bring that up? Because it's easier to find the derivative of 3 terms than it is to find the derivative of one big fraction. Because what's going to happen in the first fraction with my x's? That's going to be 3x. What's going to happen to them in my second one? It's just going to be 2. And now I can rewrite the third one using a negative exponent.
Plus 5.
So this one I would think of as 5 to the -1. 5x to the -1. Bringing it up to the top. Jake.
Jake,
Well,
dude.
It was right in this direction.
It was Jake. There's his phone right there. That was Jake.
And you've not been on your phone this entire time, Jackson Shivers? Let's start calling it out and I'll start taking all of them. Now it is after you spent the first 30 minutes on it.
Pretty sure it was Molly. Or AJ.
Yes, I was definitely thinking. All right, take a minute though. This is the simplified f of x. Okay, see what you can do with finding the derivative of each term separately. Okay? In number 11. What's the derivative of 4 sine x? 4 cosine x. Now, you might think about the second term a little bit differently. That's like there's a -1/2 in front. And then take the derivative of cosine. Okay, what's the derivative of cosine? Negative sine. You don't have to. If you understand what you're looking at and you can go directly to this, you can. That's sine x over 2. If you can do that, you can. Because the negative times the negative makes a positive, and the sign can go on top, or you can put the 1/2 in front of the sign, either way. Okay? All right, last question is 12, and then I will set you free to work on a little homework before the weekend. 12,
That's what I've been dreaming of.
okay? 12 looks a little bit nasty, but if you know how to rewrite each term, it is not actually terrible. It does. Okay, some things that look awful are not actually as bad as you want to think that they are. But take it one term at a time.
Yeah, that's filthy.
Okay? How do I rewrite a cube root with an exponent?
Cubit.
Straight up Cuban.
It's the same as a 1/3 power. A square root is the same as a 1/2 power. A fourth root is the same as the 1/4 power. We've already talked about how to rewrite the second term here. What's the best way to rewrite exponents when there's an x on the bottom?
1 to the negative x squared.
Okay, 1x to the negative squared. Yep. What about the next one?
Bring it up.
Okay, it would be good to bring it up. Okay, so that would be a -2 times a 3x to the -2. Now this one here, that's going to need a little, like one more step of work before we do anything to it. Okay, and then real quick,
Where's the fraction coming from?
what's that? Pi. What's pi?
3.1456.
Which is just a number, which means what's its derivative going to be?
0.
0. So like I'm going to leave that there, but I'm like not worried about it at all.
0 p.
Okay? The derivative of it's going to be 0. One thing I want to do before we take derivatives is clean this up. Okay? The first thing that we need to do with that, well, and in fact, let me back up a step on that one. Is that okay if I back up a step on that?
You're good to go.
All right.
You erased it already.
Before, I don't really want to think about like negative squaring something.
Me either.
So I want to go back to here. When it's on the bottom and squared like that, it might be easier to just square it now. Yeah? That 3 squared becomes 9. And that x squared becomes x squared.
Okay, fine.
So what that does for me is actually makes it a little bit easier to think about it as a fraction times x to the negative second.
I feel that.
Okay? All right, so what I would like you to do real quick, I have 4 terms, they're all in different colors. Try to take the derivative of each term individually. Okay? Last question. But here's the thing. If you show your work and like this kind of thing, it's 1 term at a time. Like I can give partial credit. If you don't get the derivative of the first term right, but you do the second, like I can help you through it. Okay?
What are all these colors?
It's like a rainbow.
What are they?
The last one.
The last one, the derivative is 0. And the second one, what would be the derivative?
Negative 2x, negative 3.
Okay. So now let's work on the other ones real quick. Jackson, put your phone away. Sit down and write it down. All right. No more sorry. All right. On the first one, power rule says, what do I do with this exponent? Bring it down front. And what do I do to the exponent?
-1.
Minus 1. So real quick thought, what's 1/3 minus 1? Negative 2/3. All right. And then green one. What do I do with the negative 2 exponent? Bring it in front and multiply it by the number that's already there. What's that going to give me? Plus 4/9. And x to the negative 1/3. Just a small amount of cleanup. Anything that has a negative exponent goes where? To the bottom. So what's that first term going to look like?
1/3
1/3.
x.
Over 3x, just positive 2/3.
Yep. Second term.
-2
Over
x to the 3rd.
Okay. The green one. That'll be the last one. 4/9x.
9x to the 3rd.
Okay. And we are done.
That's the answer?
Yep.
Nice.
Okay.
That took a lot of
Yes, but we will get better. Okay? We will get better. All right.